originally selected as a here we go. Got it. We were originally selected as a 5-year-long mission, but we asked very nicely NASA headquarters if we could have one more year to keep measuring ocean temperatures in Greenland. And you'll kind of see why as I go along. And so we actually got 6 years of observations out of our 5-year-long mission, which was really, really fun and exciting. So I'm just going to give you a little bit of an overview of what the mission was about, a little bit of what we did, and hopefully, if there's a little time at the end, answer some questions. So OMG, it's over. Yes, first of all, we finished our KDPF, which is NASA's final review back in November of last year, and officially came to an end. At the end of the calendar year last year. So we just finished. And Oceans Melting Greenland, or OMG, we flew around in Greenland for quite a bit. And saw some really amazing things. One of the things we saw this past year during our very last survey was this video that I just wanted to share with you of our airplane flying over the Helheim Glacier, which is one of the biggest ones on the East Coast and the Southeast. And here you can see we actually found a plume. We flew over the front of the glacier, and right here you can see there's this huge area of open water. This water is actually roiling up. It's water that's rising up the face of the glacier, reaching all the way to the surface, and it's pushed open a hole in the ice. We dropped a probe right in the middle of it, which was really exciting, and it measured the temperature and the salinity from the surface down to the bottom, which is what our really our major field campaign was about. This is on the right. There's the map of all the places we collected a temperature and salinity profile like this from the surface down to the seafloor using an expendable probe. But it's one that allows us to see not just the surface temperature and salinity, but gives us this profile all the way down. And that winds up being really important for the waters around Greenland. So what did we do in terms of surveys? Well, we did a whole bunch. It was a very busy 6 years. We started out looking at the sea floor. I'll talk about why in a little bit, but we did these 2 campaigns showing us where the deep troughs and the sort of underwater topography of the seafloor allows this warm water to reach in and touch Greenland's glaciers from the edges. And so the purple here was a ship survey we did with soundings of the seafloor using a multi-beam echo sounder. Then we supplemented that with airborne gravity measurements over the ocean, which allow us to kind of flesh out a little bit the places where we had the multi-beam data. So we really revolutionized the maps of the sea floor surrounding Greenland. We also, every year, we did a yearly survey of the ice. These red lines show where we collected elevation data of the ice using a radar. This we did on the Johnson Space Center's Gulfstream 3. It was a UAVSAR radar attached to the bottom of the plane that looks out to the side and sweeps out an estimate of elevation as you go along. And we were able to make elevation maps of the edges of the glaciers, right where they're interacting with the ocean for 4 different years for all of the marine terminating glaciers in Greenland. Of course, in 2019, we began using ICESat data to tell us about the elevation changes. But the GLISTEN data, this radar, gave us a really good foundation to see how the ice was changing. And I already mentioned our ocean survey, where we had about 250 per year of these expendable profilers, and it allowed us to really get a good snapshot of what the ocean was doing from one year to the next. So the basic idea behind OMG was to measure how the oceans were changing year on year, how the ice was changing year on year, and see if we could connect those two things to understand how much the oceans are melting Greenland from below. And so we had a very successful attempt to do this, I think. We also saw some really exciting things this last year. You might have heard about the rain at the summit during that same weather event. Huge melt ponds formed along the southeast coast of Greenland or the southeast part of the ice sheet, or southwest, excuse me. And during a flight from the west coast to the east coast to the west coast, we actually went back and forth in one day. We flew over some of these and posted some pictures that got a lot of attention, because you can actually find these features in some of the satellite images, and see exactly where we were flying over. But the pictures from the airplane kind of bring to life the extent of this melt event, which was certainly huge, and I think rightfully made the news. We had a great scientific output from OMG. Actually, this is a little out of date. It's 66 now publications, but in 6 years, that's a pretty good return on investment. And a lot of these papers actually were pretty well received, and had some major results, which I'll talk about a little bit. But the essential hypothesis that we had was that we would watch the oceans change from year on year, watch the ice change year on year, and see if we could show that the changes in the ocean were driving ice loss. And I'm happy to say that we confirmed this hypothesis. We were able to show through a series of papers that the changes in the ocean temperatures really were driving the ice loss. And to understand how that happens, I'm just going to play this short animation that we made to kind of illustrate how this works. So the meltwater from melting in the surface, like we saw in those earlier pictures, often finds ways to drill down through the ice sheet and essentially run off along the bottom of it. So we see this subglacial runoff sliding underneath the glaciers, reaching the seawater. And because the runoff is completely fresh, it's much lighter than the seawater, and it rises up the surface in a plume, like we saw the picture of in the early slide, and as is animated here. Now, this plume actually kind of roils, like I talked about in the picture, and it pulls in this layer of warm, deep water that is actually able to eat away more quickly at the bottom of the glacier. When that happens, it enhances the rates of calving. When the ice breaks off in larger and larger pieces and it begins to retreat, then you can actually speed up the glacier and evacuate more ice. And it's through this process that we think that the results that we've seen, where warmer water is actually able to strongly correlated with the locations where the ice is retreating, is really driven by this process. And thanks for the props on the animation. I worked for most of a year with an artist to get that to look like that. So it's been a very nice tool. But the other thing that's important to notice is that the water that's really important here is this deeper layer of warm and salty water, which is actually sitting underneath a layer of cold fresh water. And the reason it's like this is that the warm salty water is actually from the Atlantic, the saltiest ocean. The cold fresh water is from the Arctic, which is the freshest ocean. And even though it's warmer, the salt difference matters more, and that's why the deep water is heavier and it sits below the layer of shallow water. And this winds up being really important if you want to try and predict how this process might play out in the future, or at the very least, monitor what's happening as you go along. And so in a sense, you can think of this warm water as kind of a black box, because We can't really measure it from space. Remote sensing won't tell us the temperature 200 meters down below the surface. And so you really have to go there and put a thermometer in the water to see how these temperatures are changing. Now let's see if I can get just to give you some sense of the impact that we had in terms of how we measured the oceans and their sea floor. This is a picture of the coastline and the bathymetry, the seafloor depth along the coastline, sort of before OMG started. And you can see all these brown areas where we just kind of think, well, it's shallow. But if you then go to what we did after OMG, after these major surveys, you can see that actually the seafloor depth is much deeper in general along the coastline, and that it's riddled with these troughs that really allow the warm water to reach all the way in and touch the glaciers. And I see that Matthew is on the line. Morligam, I think I have a slide in here on bed machine, but he's been amazing at absorbing all of the observations that we have into bed machine and producing these amazing maps of the seafloor that have really revolutionized our knowledge of how the oceans can interact with the ice. And I'll just breeze through a couple of these things because I don't want to take too much time. But we also saw a major change in the sort of most famous glacier in Greenland, Jakobshavn, known locally as the ICESat Glacier. It has a couple of different names, actually, but ICESat is very close by. We actually saw this glacier begin to grow in the first few years of OMG. It actually advanced and got thicker. The blue here in this color map shows the ice getting thicker in 2016 to 2017, 2017 to 2018, and again in 2018 to 2019. And every year it's getting thicker by about 20 meters. And this came from the ice survey that we had. And so we started looking at the ocean temperatures, of course, right away. And one of our more important papers that got published showed that actually that this growth coincided with the arrival of very cold water that hadn't been seen in Disco Bay near this glacier in over 20 years. And incidentally, that's about how long the glacier had been growing. So we found this very strong connection between Greenland's largest glacier and the conditions offshore in the ocean. And then our sort of rock star graduate student and now postdoc at JPL also published on the impact, a similar kind of analysis. But really, instead of just looking at one glacier, he looked at all the glaciers around Greenland and found that the ocean warming, or cooling as it is, has a very strong impact on the retreat rate of the glaciers. And that if you simply ignore the impact of the ocean on the glaciers, then you can underestimate the ice loss by a factor of 2, the ice discharge by a factor of 2. So the ocean's clearly playing a very important role in the changing of the glaciers at the edges. There was also another paper I don't have a slide on, but looking at projections and found similarly that if you don't include the ocean component, that you can really dramatically underestimate the amount of ice lost in projections as well. So just a little food for thought before I wrap up here. I think one of the things we really found is that, I said the hypothesis is confirmed. The oceans around Greenland are definitely driving ice loss around the edges. And now that OMG has wrapped up, we're going to kind of go blind to this water mass around the edges of Greenland that's so important for projecting how the glaciers are going to change and even understanding the changes that we see. And so we looked a little bit at, we did a few experiments in the last couple of years with different kinds of ocean data collection. Instead of just one-time use profilers, we dropped some of these floats. These are sort of like the Argo floats, if you're familiar with the Argo array in the open ocean. It's the same instruments, but we wound up being able to put them on the shelf, and actually we're able to have them persist for through the winter. So they dive down, they come back up. If there's sea ice there, they just dive back down again and wait 3 to 5 days and then collect another profile. And they can do that all winter long. And then eventually when the ice melts, they can resurface and then return all of the data back at once. And we were able to really see these amazing estimates of the seasonal cycles and the changes in key locations on the shelf using some of these data. So they're almost like virtual ocean moorings, you could call them. So we're really pleased with the success of this, and what I hope is that in the long term, we'll be able to build an observing system that includes those and continues to monitor this really important water. I've already probably run over, so I'll skip through the outreach, but we did a really amazing job at connecting with people locally last year, in particular during our last year's survey. It was incredibly satisfying and something I really wish we had done a lot sooner, but we connected with a lot of school kids all throughout Greenland, and gave, I think, something like a dozen lectures to local school children in different cities, several of them in Nuuk. This wound up being a really major accomplishment, I think, for our last year. And so I kind of said all the things I wanted to say. I won't go through the summary. I'll just wrap it up. And if anybody has any questions or if I'm out of time, either way, all done.
Fantastic. Thanks, Josh. Yes, in the interest of time, I'll ask folks to drop their questions in the chat and we can get to them in the discussion afterwards. But while Joe is putting up his slides, I will kind of take the opportunity to ask a question. So this was a fantastic synergy of airborne and ocean-going vessels to collect all sorts of data. But is there one particular data set that you wish that OMG had collected that you didn't, that would have made this, this data set even more robust?
Yeah, I think there's a really important opportunity for actually using data collected by locals. The fishing community there collects a lot of data and is in contact with this deep water quite a lot. There's also a big effort by the Greenland Institute to fill in a lot of the gaps in the seafloor map surveys that we made. And so I think just connecting more with the people that are there would have helped us build a more robust observing system. Now, once OMG ended, right now, I really wish we had a better program for continuing those deep ocean observations and expanding some of the seafloor maps. So I think the thing I really would have wished was that we engaged a little more with the local people from the very beginning, scientists and citizens.
Great, thanks. Yeah, I know that's something that both NASA and IARPC are very much involved in promoting more as we move into this next Arctic research plan. So great, thanks, Josh. And yeah, folks, if you've got any questions for Josh, feel free to leave them in the chat and we'll get to them after Joe's presentation. And so, yeah, thanks, Josh. That was a great recap of OMG, but now we're gonna move to just an airborne campaign talking about Operation IceBridge. So Joe, take it away.
All right, can you hear me?
Yep.
And can you see these slides? Yep.
Yep, looks good, thanks.
Okay, great. Okay, thanks Caitlin, thanks Josh. I was the project scientist for NASA's Operation IceBridge in the latter third or so of It's 13 years of operation. And as OMG concluded in 2021, so did IceBridge in April. And we made our formal presentation to NASA. And what you'll be seeing here today is an abbreviated version of the presentation that the Project Science Office, myself and others, put together to summarize the work of hundreds of people over the course of 13 years since 2009. And just to discuss some of the lessons learned in the context of other IARPIC discussions going on as well. So IceBridge began in 2009, and Caitlin mentioned this earlier. It really was driven by the realization that ICESat, the original satellite laser altimeter, was failing, but its measurements were proving very valuable for understanding mass balance across both ice sheets and glaciers. And in the final phase of ICESat, that degradation happened relatively quickly. And so there was a search for an alternative mission led by NASA that could fill the gap, so to speak. And a couple of satellite missions were considered in this regard, but ultimately it was just deemed more cost effective to have annual multi-instrument airborne campaigns that eventually came to be known as Operation IceBridge, bridging the gap. And so that led to this 13-year mission that ran from 2009 to 2021, that in sum total cost was about $180 million over the course of those 13 years. And there was a council, so to speak, of expert cryosphere scientists that were put together to determine what the programmatic goals of that mission would be at an early stage, and these were later refined. Priority there was to make airborne altimetry measurements over ice sheets and sea ice, and to extend that record of observations made by ICESat. Link them to satellites that were either had existed, ICESat, or were going to exist in the near future, ICESat-2, CryoSat-2, monitor rapidly changing areas, and also not just collect altimetry data, but also collect other data that is going to suitably contextualize those data and make them more useful. And so that led to these multi-instrument suites that we used. Those programmatic goals led into a whole series of tasks for a competed science team, what exactly the science questions of the mission were, what the data set requirements were, and ultimately those led into 27 level 1 science requirements. I won't go through those today. You can look those up in papers, but those ultimately determined how we assessed how well the mission did for its various goals that it set out for itself at the beginning. So what did these campaigns look like? They were operated on board a variety of aircraft shown here on the right. We ultimately conducted 64 campaigns in both the Arctic, Antarctic, and Alaska. And these were either a few weeks long to several months long, or typically springtime campaigns in the Antarctic and Antarctic, surveying both repeat tracks, again, with that primary focus on altimetry, but also new tracks over new terrain as priorities determined by the science team shifted towards areas that might be changing more rapidly or that we had a limited understanding of. There was a set of campaigns that was run by Chris Larson at University of Alaska Fairbanks, who did summer and fall Alaska campaigns, primarily laser altimetry, but also some radar sounding and other during the later years. I mentioned the satellite altimeters. We often tried to coincide. Sometimes that occurred simultaneously, as in we can't fly as fast as the satellite, obviously, but other times, but we did attempt to keep up with it to be more or less synchronous with the satellite. This was mostly run the Project Science Office out of NASA Goddard, where I'm based. And again, we had a variety of instruments and a variety and 3 iterations of the science team. Here's a visual summarizing what our instrument strategy looked like. At the core here, we have in center image, we've got the NASA P3, which was our primary Arctic aircraft, which is collecting laser altimetry data and also radar sounding data, just shown visually here, but other types of data as well, in particular imagery and oftentimes gravimetry as well. The altimetry is shown here on the left. We operated a variety of laser altimeters, primarily the airborne topographic mapper run out of Wallops Flight Facility, which can survey this nice swath whose width is comparable to the altitude of the aircraft, and then also a narrower swath at finer detail. And on the right, just an example of some of the radar sounders, almost all of which were operated by the University of Kansas when we're operating primarily on NASA aircraft to measure the full thickness, as shown on the top right here, intermediate depths shown by, that's done by UHF radars, and then finally SHF radars to measure snow radars to measure snow thicknesses in the top 50 meters or so, depending on where you are on the ice sheet. Here's a GIF that summarizes where we flew just in the Arctic over the course of the 13 years, and it's going to loop through, and you can see the evolution in our thinking, how we surveyed primarily out of Thule Air Base and Kangerlussuaq when we're in Greenland, and then also Fairbanks for sea ice, which we would cross back and forth between Thule and Fairbanks almost every year, and or Fairbanks and Barrow, pardon me. Or Reykjavik, pardon me. And then OIB Alaska, run by Chris Larson, which would typically operate out of half a dozen or so bases in Alaska, but just a couple of those are highlighted here, and primarily flying repeat laser altimetry. Thinking about things from the IARCtic perspective, I want to emphasize here some collaborations. I'm going to talk about interagency collaborations and then also international collaborations as well that the IceBridge undertook. On the interagency side, that required interaction with a vast number of other agencies, many of which are listed here. And most of the credit for organizing these and keep track of them goes to the project managers that we had on the mission, who did fantastic jobs of keeping track of the various needs of these different other agencies and requirements as we prepared for each campaign. Together, I want to highlight here Department of State, NSF, and NOAA, and USAF, the Air Force, who really made our Arctic campaigns possible and successful across across a variety of terrains and logistical challenges. We also work closely with Canadians when we, the Canadian agencies when we're working in the Arctic, in particular Environment and Climate Change Canada, and also the Canadian Space Agency. Those enabled us to focus on occasion, as you saw on the map slide, on the Canadian Arctic archipelago, the glaciers there, and also some of the efforts to understand the sea ice environment that Environment and Climate Change Canada were undertaking. We did overflights of some of their survey areas in the Arctic Ocean, or next to the Arctic Ocean, I should say. And also their weather imagery proved absolutely critical for us to be able to do what we did in the Arctic and be successful. Because most of the time, IceBridge was operating relatively low altitude, 1,500 feet. And in order to do that, we needed to know that we had the cloud conditions that were going to enable, in particular, our laser altimeters to succeed on a regular basis. We also collaborated extensively internationally, again, focusing here on the Arctic, European collaborations, underflights of ICESat-2 and the Sentinel-3 A and B, and NVSat. In order to make those happen, we had to be able to understand their orbits well, the timings, and so that required collaboration with ESA. And they also undertook their own validation campaigns with their satellite aircraft, and we where possible, I think happened a couple of times, we were able to compare our instrument suite against theirs. And while working on the Greenland ice sheet, several different groups were, European groups working there, and we were able to do overflights to help contextualize some of the data that they were collecting in situ. Data products, NSIDC was OIB's DAC. This is where you can find all of the data products that IceBridge has archived. This was quite a challenge to get that all up and running, because prior to IceBridge, NSIDC didn't serve a lot of airborne data. And so we really upped the scale on that. And also because of NASA's mandate for open data, we also raised the standard of how large quantities of airborne data for these types of polar geophysical surveys were shared. Previously, some were either hard to access or not shared at all. And IceBridge really changed the game in that regard. Just a couple of scientific highlights. Josh did a great job of summarizing OMG's focus. IceBridge, at last count, we had about 660 articles. This was last year that used IceBridge data in some way. I'm sure the number is higher now. So I can't possibly do justice to all of that. Just highlight a few of those here briefly. In terms of understanding the Greenland ice sheet, obviously the altimetry was essential for monitoring changes in many different outlet glaciers and better understanding the thinning and, as Josh showed, in some cases, the thickening pattern that could happen as some of these outlets responded to, especially to external forcings, such as ocean temperatures, and how those evolved over time. And so the longer your temporal record, the better you're going to be able to do that. In the center here, we've got IceBridge's contributions to understanding of bed topography for the Greenland ice sheet via bed machine, which Josh mentioned earlier. And so here, not focusing not so much on the seafloor bathymetry, although we did collect some gravity data to help with that, but primarily the radar sounding data that helped contribute to these syntheses. And so here you see what IceBridge was able to contribute to bed machine version 3. There's now a version 4 out, I think. And on the right, that topography data, some of that altimetry data, that all helps go into these assessments of mass balance. So you've got Jeremy Mouchinot's 2019 here. Question? Or someone, hot mic, no worries. So important in a variety of contexts for understanding the state, the boundary conditions of the ice sheet, and the state of its mass balance. In terms of glacier surveys, those were typically flown with much smaller aircraft, again, primarily focusing on laser altimetry for most of the IceBridge era, but they helped us truly understand that the negative surface mass balance is likely what's dominating the retreat of most Alaskan glaciers, as shown in this 2015 paper by Chris Larson. By using lower frequency radar sounders, IceBridge was able to help measure much thicker ice than has been in temperate ice for these glaciers than is typically possible due to their temperature, water content, et cetera, and crevasses, et cetera. In terms of understanding Arctic sea ice, less of a focus for this group, but the widespread surveys, the repeat surveys that we collected really enabled these sort of basin scale evaluations of some of these properties that are crucial for contextualizing not just the extent of the ice, but how it's changing in the vertical sense too. So understanding its freeboard in the context of how thick the snow overlying the ice is, and then what the total ice thickness is as well, and how those have changed over time relative to earlier measurements. I want to highlight some of our educational efforts. Josh fairly pointed out that in terms of connecting with schools in Greenland, IceBridge didn't do a particularly effective job in that sense because we were typically only based in Thule and Kangerlussuaq. But we did have engagement while we were in flight with a variety of K-12 students in many countries through this mission tool suite that NASA's put together. And that allowed us to have these text-based chats with more than 11,000 students over the course of the mission. We had a variety of media engagement over the years. We were very fortunate to collect some relatively high-profile government officials, national and international media crews to come along with all sorts of media that were collected and shared widely. We also produced a lot of our own media. Goddard has a production facility, and we now have at this link here, you can access all of the videos that NASA collected, including some B-roll that show some of the animations for various studies and sort of campaign snapshots over the years. So what's the outlook now scientifically after the end of IceBridge? Well, ICESat, when we wrote this last year, ICESat-2 was operating well. It continues to operate well. It's exceeding expectations in how well we want to be able to map altimetric change. And it could potentially function for decades. So we did get there. We did fill the gap as was our original mandate. And we, through some of the early measurements that we collected, we helped set the stage and the motivation for new polar airborne missions like OMG that could go out and collect data that we couldn't collect because of our particular foci. It's worth pointing out an altimetry gap could still rise, but over the course of IceBridge, we developed some the tools, the knowledge base, and also some new aircraft came online that could potentially help make this easier to rectify in the future. There's still a variety of cryosphere challenges out there. Josh mentioned one in terms of now going dark. There's many parts of the Arctic Ocean that we're still relatively ignorant of in terms of its sea ice behavior. There are still large swaths of the Greenland ice sheet that are relatively poorly surveyed, and most Alaskan glaciers are unsurveyed in terms of their thickness, and we have poor constraints on their snowfall. I want to turn now briefly, given the time, just to some quick lessons learned programmatically wise and maybe relevant for the IARPIC audience as well. In terms of reaching out to the community and public outreach, we did this in a variety of international forums for open discussions associated with flight designs, and there were really no restrictions on providing input, but on a fairly regular basis, we would hear that it was unclear on how to provide suggestions to the team. We had an online tool for that for a while. We would mention especially to junior scientists, that this was something they can engage with. But it's clear that we need to continue to innovate in reaching the scientific community for input to flight designs. Because I would say over 80% of suggested flight design modifications we ended up incorporating in some form in the surveys that we did. We did various updates via that as internet access improved in polar regions, got picked up by social media, and people had insights into rarely visited places, but we had no formal rules associated with that. And so formalizing that process a little bit and archiving them better could be helpful for the future. In terms of distributing data, we not had a nominal 6-month delivery time, but for almost all instruments, that was never met, and in that time frame. And so there, it's worth reconsidering for particular airborne data sets, whether that 6-month time frame is genuinely helpful, and reassessing with instrument scientists what's going to be realistic for sharing what are sometimes relatively complex data sets, like some of the radar sounders, in a realistic time frame and keep everyone happy. We had these quick look sea ice products. We didn't have any for land ice or for glaciers, but they were difficult to get out quickly, as quickly as we would like for sort of seasonal ice thickness assessments. So we should really reassess how valuable quick look products are in this context, and whether they were included in level 1 science requirements, whether or not that should be the case going forward. Occasionally, we had internal preliminary data releases. Those almost always just ended up causing problems and were less helpful for internal assessments than the external problems that they cause. And finally, I do want to make a note about the sort of professional environment. I stand before you, a white male, and Operation IceBridge was primarily male and white. And we were primarily operating very far from the employer resources to potentially deal with any harassment that occurred. That isn't to say that we believe that was a large problem associated with IceBridge, but it does leave the women and underrepresented minorities more at risk of that in these austere environments. So as IceBridge progressed, this became more of a sort of an issue that was at the forefront of our minds. And so many of us undertook bystander awareness training, especially at Goddard, but it wasn't mandated across the mission. And in fact, we really didn't have a good sense of the gender and the racial makeup of the mission because it wasn't something that we actively worked. We knew that we had done a formal survey of. So that's something we think should be encouraged for missions in the future. And finally, our UPO, although we'd like to think we did a good amount of it and we reached a relatively large audience, it wasn't really targeted toward underrepresented communities that we're hoping to bring into science as well, and to allow the science that's done in the cryosphere to represent the communities that exist within the cryosphere as well. So yeah, with that, I will stop and take any questions.
Fantastic, thanks, Joe. I guess I'll ask you the same question that I asked Josh to kind of kick off the discussion here. I know that IceBridge had a pretty wide suite of instruments and data products and observations that it was collecting, but what do you think was one thing that you wish would be added, I guess, to the OIB data record that wasn't there?
Well, actually, I would flip it around to it would have been great if we had also done some ocean sounding along the lines of what OMG did. I'm not saying that our mandate would have entirely shifted, but clearly we were operating in a lot of the same areas and often at a slightly different time of year, which would have challenged the measurement. But especially in Antarctica as well, we're going to places that very few groups have been able to access on a regular basis. So if we had been able to get a sense of what water temperatures were like in those regions, that could have been very helpful for assessing how especially those outlet glaciers are going to be changing in the future, but also give us a baseline for the state of the ocean, which is very important to the sea ice as well.
Fantastic, thanks. I know Josh has been answering a handful of questions over in the chat, but is there anyone else that has any questions or comments for Joe or for Josh that they'd like to raise now, either out loud or in the chat, and we can read them out loud?
I have a question for Josh. So, Josh, in the context of connecting more with communities, you sound like you were aware of NSF's Navigating the New Arctic program, and how I can't claim to have a perfect understanding, but it does seem to more formally aim to include local communities as well. And what is your what is your sense of that program? Is it heading the right direction?
I'm not super familiar with the program, but I think what we found in our last year was that when we took the time to go to a local school or reach out and give a talk to local people, even though sometimes it was challenging, there were language barriers and other things, it was appreciated, and it actually kind of opened doors for us that we wouldn't have thought of or realized otherwise. There were I think there was just there's a sense, especially in Greenland, that there's this kind of hit and run science, they call it, where the scientists come in, collect the data, and then leave, and don't really at least don't have a tangible, clear connection to the people that live there. And so I think what I really wish we had done is that same set of talks, but the first year, and then we could have developed a little bit more robust relationship with them, I think. So I think a lot of it, at least at the beginning, this may sound silly, but a lot of it is just showing up and being willing to engage. That's the first step, and it's I think the most important one. Of course, you know, we want to help the communities and you know, translate our science into stuff that benefits them as well. And that's a hard part, and it's a long, you know, it's a long, as you know, science is a long, slow process, as we all know. So it's slow, but I think if you start it early, then it's easier to connect with people, and you avoid that sense of you know, just running in and running out as fast as you can.
Yeah, I totally agree. Yeah, thanks for that. Yeah, that was you know, we through IceBridge, because of our larger aircraft, it was easier for us to bring ride-alongs from the local community. But I mean, there you're connecting with at most 1 or 2 people. And I think one of our regrets for IceBridge is we didn't, especially in Kangerlussuaq, we could do this a little more easily. And Thule was not connecting with that local community as effectively as we could. We certainly had vendors, obviously, that we interacted with quite a bit, but not the whole community.
It was actually one of our vendors in Kangerlussuaq that got us the talk at the local school there. And one of those pictures that I flashed up was Ian Fenty with all the kids, and they didn't get to fly on the plane. That's actually gotten really a lot more challenging because of sort of internal NASA politics, but it certainly made us feel a lot more welcome and better taken care of there when we were willing to, you know, give a local talk.
Cool, thanks for that context. Anybody else before we move on to some announcements? All right. Well, thanks so much, Joe and Josh, for sharing lessons learned and highlights from both of those missions. I know that those data sets are super important, especially for this community. So thank you for coming today and for sharing. Just another quick update from the Glaciers and Sea Level team. Our next meeting will be on February 10th. And that'll be an opportunity for us to get together and talk a little bit about the new Arctic research plan, which is spanning from now, 2022, through 2026. The new Arctic research plan is structured a little bit differently than the one that IARPC was operating under over the last 5 years, and has 4 different priority areas. Those priority areas being community resilience and health, Arctic systems interactions, which primarily the Glaciers and Sea Level Collaboration team would probably fall under in terms of our activities, sustainable economies and livelihoods, and risk management and hazard mitigation. So that meeting in about 3 weeks will be an opportunity for us to come together and talk about some of the things in terms of science and interactions that we want to, as a team, sort of tackle over the course of the next Arctic research plan. And Joe and I will be getting together with Meredith and the rest of the IARPC collaboration team leads in the next couple of weeks and thinking about what we want to present at this meeting over the course of the next year. So if you're there's a particular theme that you think that we should be tackling over the course of the next calendar year and presenting to this group, please let us know and we'd be happy to add you to the calendar. Joe or Meredith, you want to add anything onto that?
Well, I do want to echo that last point, Caitlin. It's a great one. It's not something that we've actively done in the past, but we're definitely open to community-driven topics for organizing speakers. We usually can come up with a pretty good sweep of ideas, but you know, responding to the community is definitely something we want to do as well. I do want to mention, for those who are interested, the talks are going to be on the IARPC website. What we've presented today will be on YouTube as all IARPC presentations. And I forgot to mention, because I accidentally skipped my last slide, what I've shown is it discussed in much more detail in a 40 author, 60+ page paper in Reviews of Geophysics from last year. So you got a flavor of what IceBridge did, but you can get a much fuller scoop in that paper.
Cool, thanks, Joe. Meredith, anything else to close us out today?
I put some links in the chat to the recording and then to the Arctic Research Plan. And that's all from me. Thanks everyone for joining.
Fantastic. Thanks, Meredith. And thanks everyone for joining today. Thanks again to Joe and to Josh for presenting. We'll be in touch and we hope to see most of you on February 10th.
Thank you for hosting.
Thank you, Caitlin. Thank you, Meredith. Thanks, Josh.
Thanks, everyone.